uh, the this technique really based on the TMD concept we have. However, now if you look at the textbook, most of textbook, control textbook, they are dealing with the called first order dynamics state space equations. We'll talk about that later too. But the transformation from the second order dynamic equation to first order form, like what you learned about the couple of weeks ago, we know that transform from second order to first order, most likely you lose the physical insight. For example, your transformation metric, your first order equations, the metrics won't be symmetric anymore. But the second order equations, mass matrix is symmetric, stiffness matrix is symmetric. So you still have those kind of nice properties. Now, how can we design a controller using the second order dynamics equations rather than the first order? That's the motivation of this called the AVA, the concept. So we did just look at the second order equations. You look at this, all the parameters have physical interpretations. Like W is the physical coordinate, unless you transform to another coordinate. W is a physical coordinate. Mass M is a mass matrix. That mass matrix is positive definite. And K, stiffness matrix, the stiffness matrix is also symmetrics, and is most the cases they are also positive definite. And we know that if that's the case, then the system is stable. So we're going to use that. So how can we take advantage of this kind of the second order form? Now that's what we are going to talk about. All right. Let me just close this comment. All right. So the approach will develop the active model independent controller. We'll explain what do we mean model independent. The model independent controller for the vibration control of the flexible system. Now, if we look at this, and look at that equation again. We'll take out those equations. Let me just do this. All right. Let's go back here. Okay. What do we mean model independent? Okay. This W plus W dot plus K W equal to BU. All right. If we have N larger is positive definite, and this is also positive definite, and then K is also positive definite, then this system is stable. The system is stable. It's not only stable, it's asymptotically stable. So as long as this is satisfied, this is stable. So it doesn't matter what kind of M or Z, K, as long as they are positive definite, then that system is stable. So if I can design a controller like that, the K, for example, then they are all stable. Okay, now let us go back here. And we already defined this. All right, this is all we have talked about that already. And I just refresh your memory because we are going to use this kind of properties. A positive definite matrix means all eigenvalues are positive definite, and this is just proof. The eigenvalue problem n times psi equal to cap psi lambda, and lambda is your diagonal lambda 1, lambda 2, and lambda n. Assume that this is diagonalizable. Fortunately, all the system metrics like this, n, zeta, k, if this is positive definite, and this positive definite, this positive definite, then the system M, the vector matrix here, the symmetric matrix is always diagonalizing. Okay, so there's some special property here. We need to talk about that. Any symmetric matrix is diagonalizing. In other words, any symmetric matrix you can transform to a diagonal matrix. Other symmetric matrix. Also, all the symmetric matrix, the eigenvalue and eigenvectors of a symmetric matrix is not necessarily positive definite. Symmetric matrix are real. All right. So, mathematics is always positive definite. Because mathematics is always positive definite, that means they are always diagonalizable, their eigenvalues are real, and also their eigenvalues are positive. So lambda 1 larger than 0, lambda 2 larger than 0, and lambda n larger than 0. All eigenvalues are positive. So that's the property of the positive definite matrix. All the eigenvalues are positive. The eigenvalue, eigenvectors of any matrix, symmetric matrix, they are all real. It has to be like that. Okay. And plus, the eigenvectors are all orthogonal too. All the eigenvectors are orthogonal of symmetric matrix. All eigenvectors are orthogonal. Orthogonal. Okay? That means the psi matrix here, the psi matrix on psi is a diagonal matrix. And they can normalize it, so become identity matrix. We call normalizations. Here, if we normalization, there's normalization involved here. No. The normalization means each column of this psi matrix, the length of each column is 1. If that's the case, then if normalization, then transpose equal to psi inverse. Right. So this is why I can have the psi inverse become the psi transpose. Any symmetric matrix you can find a transformation matrix like that. That not only diagonalize the matrix, also they will be orthogonal, and also you can normalize it, and so that psi inverse equal to psi transpose. And so this is the positive matrix, the typical property like that. And so, all right, the spring and death part. We looked at that before already. And let's look at this. And the frequency is square root k over n. And if u equals 0, and this is homogeneous solutions, and so we can have the transient response like that. That's the transient response. Wt equal to W0 cosine omega t plus omega 0 dot omega sine omega t. Assume our initial condition W at t equals 0 equal to W0, and W dot at t equals 0 equal to W dot sub 0. If that's the definition, then Wt equal to W0 cosine omega t plus W0 dot over omega sine omega t. And this is the solution. Well, we'll see why this is. These solutions, I'm going to show you that this solution won't be unstable, right? Never be unstable. Because it's a sine. It won't grow. The response won't grow. It won't go up. It just oscillate in that sine or cosine in that frequencies. But a simple mass system. All right. Okay, now let's go to our feedback control. What do we mean feedback control? Assume we have a sensor. We have a measure device. That measure the W. That measure Y. That's it. The sensor gives Y. And this sensor gives you what? If I put a sensor there, they likely give you what kind of signal? They give you the volts or amps, right? Agree? If you use electrical device, they give you what? They give you, of course, they give you volts and amps. But however, you can convert it. Say 1 volt equivalent to